Okay. Now, yesterday we talked about waves can be bent. And there are a few ways in which this can happen. And some, we talked, I think, about riptides, at least the very beginning of the idea of riptides. And we're still focusing on refraction. Now, just as a quick reminder, when you watch, not a reminder rather, an observation, anybody in here ever been on the beach and you watch the waves crash? Okay, how frequently is it if I'm a wave right now and this is the shore, do I come in perfect square to the shore and just crash straight down? Not typically. Now, it can happen. It's rare, but it could happen. More often than not, what happens is it comes at an angle and you see the wave like going down the coast, right? It crashes and then it keeps crashing further down because that wave is breaking at an angle. As we look at this, you are seeing the effects of waves being refracted by a variety of the different things that exist out in our bay here or elsewhere in the ocean. For the refraction that we're concerned about, there's a really easy way to think about this, and we're going to draw a simple picture. We're going to say that this is just a picture of a coastline. And I'm looking from above, so here is just our square picture. And then let's hypothetically say that all of this right here is the shore. So we have a shore line here. All of this is ground, it's rock, it's whatever you want to call it. It's not water. Okay. As we're looking at it, there's a few different things that we can talk about with this. If this were an earth science course, the focus would be on why is the shore shaped the way that it is. It is what it is. We're just going to accept it for here. Now, waves in the ocean. It's certainly possible that their crests, if we looked all the way out, they look like this. And they could be exactly parallel to shore. We're going to work within the situation where they came in perfectly and they did come in parallel initially. Now, each little blue line that I'm about to draw, we're going to consider the crest of a wave. So it's just the top part. So if I wanted, here's one wave all the way out here. Here's another wave here. So that's just the next crest. This would be your wavelength between the two tops of two successive waves. Now, based on the shoreline that we have here, and I know that it could vary a lot, but if I asked, and random number's fine, if I asked the depth right here, somebody throw out a number. There's no right or wrong.
35 feet.
35 feet. Okay, I'll accept it. If I check the depth here, do you think it's going to be 35 feet anymore?
No.
Why?
The shore is like, yeah, there's more land there, which means that there's probably a less of an angle up for the waves. So it's like,
I agree with you. I'm going to reword it just a little
yeah.
bit. There's land underneath this water here. And it's a really low depth because this is right off the coast. It's a really low depth right here because it's right off the coast of the land, right? So if we think about waves coming in, out here, it's certainly possible that we have these two waves being represented by deep water waves because the water's deep enough. However, as we get in and we start looking, this wave right here might be the last one that's kind of normal. Or, I'm even going to make this the first weird one. Is it possible that we have significantly less depth here? What happens to a wave when it starts to rub against the bottom? Does it speed up or slow down? It slows down, which means this wave, maybe it's all the way up here right now, but as we get closer, it's going to start doing something like this. The wave has to bend to meet the shape because it rubs on the bottom of the ocean floor right there, and it slows down. Now, as this happens, we get more and more shallow, and our waves start to get more and more pronounced as we go through. In this situation, we can see that these kind of ebb and flow back and forth. The shape of the coastline dictates the waves are going to crash really hard right here, right on this peak. But they also crash right there because of the way the land is. All my energy gets focused right here. Now, these waves, they get bent, right? It's a whole wave and it meets the land and some of it slides in. These waves are now at a bit of an angle to the shore, which means if I watch this wave keep crashing, if it starts crashing here, it'll crash here a little bit later in time. Here a little bit later, we see that there are that slanted, that angular wave, and they come in and spread their energy everywhere. Now, as we go through this, what winds up happening is if we just look at the path of water, and I know you don't have a bunch of colors to do yours, right now I'd say the wave at here is traveling straight forward, right? Here, what's it doing? Is it still going straight forward? And I can rephrase this. I'm trying to avoid getting way too mathy with it. That wave, this is just going to be a mathy statement, okay? Waves propagate perpendicular to their how do I want to word it so that it doesn't get too crazy? I'm just going to say the direction of the wave is perpendicular at that point. So that's the direction the wave's going. Right here, if I drew it perpendicular, is that perpendicular? It's going to start doing something like this, right? Now, here, same thing. If I just go a little bit further, realistically, I'm just not a great artist. It's also going to be curved. The same thing, but in the opposite direction is going to happen here. A wave traveling straight toward the coast starts to bend, and now it starts to turn a little bit in, right? Are you guys okay with that? Okay, I don't want to draw a billion arrows, but the closer I get here, the more it starts to look like this, right? Like the more sideways they're going to start looking. And I'm going to start seeing that in this surf at the very front, we get a lot of water that starts to push this way. On this side, it just goes the opposite. All this water that's slowly pushing at an angle, the angle gets steeper and it starts to push this direction along the coast. Are we in agreement there? Now, if conditions are right, this is what causes those dangerous skull signs that happen. I get a lot of water flowing in doing this. And a lot of water along the coastline being funneled in like this. When they meet, they have energy. Which way do they want to keep going?
Keep going that way.
They want to keep going. Which means as I look at this picture, as I get nearer and nearer this point, I'm getting more and more energy, not only crashing in, but pushing back out. At some point, when conditions are right, is it possible that this energy overcomes it? And all of a sudden, you get a new current that instead, like every other wave there, going into the shore, blasts outward. This is a death sign. Like, this is terrifying. I've never been in one. I'm kind of scared of it. I'm scared of the ocean anyway. Ocean's big and powerful. With that in mind, if you've never been in a rip current, anybody here ever been in a rip current?
I've been.
Riptides. Okay. Thank goodness if you never have. If you're ever swimming somewhere and you realize that, man, I'm getting pulled out to sea, how do you fight this?
Yeah.
You float in your back so you're in the middle of the ocean and then you drown.
What? I thought that's what they always taught us, like to float on your back.
If you're in a riptide, not the option that you should go with. Dwayne.
Don't you like swim like opposite?
Yeah. What people do and why people die in these is they're not huge. They're like legitimately 5 to 30 or 40 feet wide. They're not very big because we get all of this. I'm just going to draw it kind of large here. We get this flowing back out to sea. Now, if you get caught in this and you just float, eventually, I can't scroll down anymore because I'm out of it, but you're going to wind out like here, all the way down at the bottom of the screen, right? And these waves, because of the circular motion that waves make, they're not going to bring you back in. You're just going to bob up and down until you don't bob up and down. Now, the better way to break this, Dwayne, say what you said again? Or James, who said it before? It was Dwayne. Dwayne, what was your suggestion?
Like, I don't know what's it called when you swim, like,
Perpendicular to the current. If you realize all of a sudden that you're sitting in the water and the shore is getting further and further away, because it can be hard to tell when there's a bunch of water moving around you, you turn parallel to the shore as best you can. You swim straight that way or straight that way, you're going to get out of the riptide and you're going to be able to swim back in as long as you recognize it, before you get way out there. Okay, now, water obviously gets transported up and down the beach due to this, right? Anything else that gets transported up and down the beach due to this water current that flows? Like if you walk down a front beach, it's perfectly flat the whole way, all the way along the road, right? No, it's not. I just spoke with conviction. I see a lot of grooves, like it comes in and out, and you see where it happens. Thanks. Thank you. Appreciate it. Okay. Now, if we went and took a picture right now, and I went a year from now and took the same picture, are the grooves going to be in the same places? Why? They won't be. Erosion, and specifically that same current that could create a riptide in perfect circumstances, waves are strong. The ocean is strong. Is it strong enough to move all the little rocks and pebbles and stuff? And if they're getting pushed at a diagonal place, some of them inevitably wind up moving down the shore, and we see those push-out points occur in different places, just depends on where rocks happen to gather. This specific, the movement, rather than just the water, that we're going to sneak in a quick definition, and we're nearly done with this. This movement of debris and rock and like geology stuff, that's a weird way to word it. I like rock, we'll just call it that. That movement that we see along the coast of rocks and ultimately shaping our coast is what we call a longshore transport. Okay. Longshore transport. I'm not going to draw the picture again because it's essentially the same picture. But when we're looking at it, longshore transport is rather than a riptide being formed, and even if a riptide is formed, it is the movement of water and sediment So movement of sediment. Not a longshoreman, although longshoremen literally move stuff up and down the coasts. So yes. Movement of sediment due to what? So it's due to erosion. What cause? And the waves, like, it's not just the waves. It's something specific the waves do. We bend their shape when they reach land because they all reach land at different. Say it again. Boom. Due to refraction. And I'm going to say along a coast. Okay. The same picture that generates riptides is also responsible for shaping the way that our coastline looks. Cool. I don't want to draw the picture again. I don't think we need to. Everybody cool with that? Okay. The next little piece What's up? I know how to spell. I really do, I think. Anything except French-derived words. Coast. Weird. Okay. Sometimes we get really big waves and scary waves that cause and like havoc to entire countries and hundreds of thousands of people. They're tsunamis, right? I've only been in a part of a couple tsunami warnings. I've never seen a real tsunami, thank goodness. What causes, tsunamis? Earthquakes, pretty common. The other one that we saw, I'm just going to say the movement of Earth, just in general. And it doesn't necessarily have to be Earth, because if you get a big enough calving glacier, oh yeah, there can be that. It can be a landslide, it can be an earthquake. It's Earth moving due to something. Now, if you were in the middle of the ocean, do you think you would be able to tell me, if you were sitting there and a tsunami goes by, would you know it necessarily?
I would know if I wasn't sure.
You wouldn't. Like, pretty unlikely that you would know it, because out in deep water, they behave as just large swells. If I have a gigantic wave, like that I'm standing on, that's so big that I can barely tell that I'm going up or down, I'm not going to be able to notice it. Okay, they are huge. When we talk about how big tsunamis are, they're crazy. The wavelength of a tsunami, there's multiple waves it'll hit. There's that first primary wave, and then secondary and tertiary, and so forth and so on. Any idea how big the wavelength can be? Like regular waves, small waves especially, like you're looking 10 to 20 feet. Larger seas, when we get 80 and 100 foot seas, you're probably looking at a few hundred feet between them. Tsunamis, any idea? Just total guess in the dark. 500 feet? More.
1,000.
Could be more than 1,000 feet. They can be up to 200 kilometers. They're huge. The amount of water that happens, and if we think about it, if I all of a sudden have a big hole on the Earth's surface form underneath, all the water that has to fill it, if it's a big enough hole, it can come from like 1,000 miles away. All that water has to move because it's all being pulled down by gravity. As a result, you get huge wavelengths, up to 200 kilometers, which is crazy. Now, beyond that, super tsunamis have happened. Hopefully, we never see one, in our lifetimes or in any of our children's or children's children's. Let's say, hopefully, no more super tsunamis. They can be real big. When we talk about waves moving, we use the word propagate. Waves propagate through a medium. So waves in the ocean propagate through the ocean. Waves of light propagate through the air here currently, but we call it as propagating. How fast do you think tsunamis can move? Like big waves, and I've never spent enough time around big waves somewhere with there's really big waves. Do big waves go faster than small waves? They go slower typically?
I'd say that. 'Cause if you think
Like,
about
go ahead.
their wavelength, right, is 1,000 feet apart compared to like 10 feet apart. I feel like you go quicker.
Yeah, I think there's an argument they can make. It probably, I think more it depends, rather than just saying it does this all the time, depends on what it's passing through, realistically. Because I can put my arms this far apart and I can walk this fast, but I can walk that fast going this far apart too. So there's some variation in there. Adam suggested a number though. He said they can go 100 kilometers an hour, or miles an hour. That's like 200 miles, 200 kilometers per hour. Do you believe that a wave can travel at 100 miles per hour through our ocean? It can. It's actually way faster. They've been recorded up to 500 miles per hour. A giant wall of water traveling at 500 miles per hour. We don't get them nowadays. Like the tsunami in Indonesia. I don't know it off the top of my head. We'll Google it. Anybody know how tall it was? Like how big its amplitude was? I also have no clue. I'm going to guess like You think 2.5K what, Adam? I don't think it was that big. I'd be shocked. Amplitude of Indonesian tsunami. We should have done Fukushima because that was a more recent one. 167 feet. That's not that big. Okay.
Check out the one
Like,
in Japan.
that's a big wave. Fukushima? What? I thought I did it. Shima wave tsunami. I don't believe you. 23 meters? Smaller. Like, those weren't very big. There's evidence, even around here, geological evidence, that we've had waves crashing on this island before people existed. Otherwise, they wouldn't be here. Hundreds and hundreds of feet high, all the way up on the mountains. Like, we see them. They happen. They have happened. They're terrifying. When I moved here initially, the number of texts that I got from one friend, family friend in particular, about tsunamis coming, like just to tease me, was unreal. I feel pretty safe here because of the geology that we live in. Like, it's not going to come from the north if it happens. So I feel pretty good about it. Have you guys ever seen footage of these tsunamis happening?
Kind of.
Oh my gosh, it's terrifying.
I do hear that
If you ever,
there's huge ones on the backside of that. Like, there's not huge ones, but they're
I believe it. Okay, so while we're looking at that, tsunamis exist. How do we monitor for them? We all went to a presentation either this year or last year. I don't recall which one it was. How do we, like, if there's a tsunami that happens in the middle of the Pacific, how do we learn about it before, you know, it hits us?
Oh, they have, what they have like buoys.
There are buoys that are out there constantly monitoring. Now, we don't have a lot of buoys, and our ocean's huge. Is like, we need to make sure that, just in general, like, there's nothing that we personally can do yet. But the more buoys, the more data we have, the better reliable, like, reaction we have to tsunamis, right? What do we do? I know we all know it, but just to check. If there were a tsunami right now, all of a sudden siren goes off, where do we go? Okay, from your house, do you know where you go?
I go to the rocks.
Cool, I don't know where most of you live. Where do you go, JB? That's where I would go. I would go to the quarry. Yep. Ski bowl is pretty common. I would go to ski bowl or haystack, depending on what traffic looked like. Cool. Now, there are other types of waves. We have deep water. We have shallow. What's a word for in between? Schmedium. I'm cool with that. Intermediate is also a good word. If it happens that our depth to wavelength ratio lands somewhere between 1/2 and 1/20th, we get intermediate waves, and they behave like both or more like one, depending on if it's closer to deep water, it's going to behave more like a deep water wave. Closer to shallow, it'll behave more shallow. Okay. With that said, the only thing we haven't talked about is a standing wave, and I'll take this over there with me. There's two things we haven't talked about: standing waves and internal waves. But let's use a couple minutes real quick. This is your free pass for bathroom break and coats and shoes and stuff. We're going to head over to the hatchery in 3 minutes.